Hey, hi guys, this is Akash Verma and you're watching Cafe IO. Today we are going to be talking about container ecosystem and its relevance in the modern ecosystem of IT deployment technologies. Now, container ecosystem is very wide and we'll talk about a couple of use cases, how that shaped up, what are the differences between the previous mode of deployments that we have and how does it work fundamentally, right? And then we'll also take a look at a couple of options like creating an application with containers, and we'll try to do a live demonstration of a deployment. So that's what we're going to be talking today. Let's just wait for a couple of more minutes for more people to join, and we should start the stream around 10 p.m. or so, like in another 5 to 6 minutes. All right, so there's four people that I see are here, guys. If you could just put in chat your names, that could help me address queries if you have anything. And welcome, guys, and do get your friends too. If you could just put a name in the chat, that would be helpful. I'll probably. Okay, so this application this time I'm trying to stream on a couple of places. For instance, this is going on to uh, we have this is currently being sent to Facebook. This is currently being sent to Twitch. This is the first time I'm trying to do a multi-stream using Melon. So that's kind of nice. All right. Can somebody just confirm and tell me if they're able to hear my voice correctly and probably if I'm showing my screen right now and or showing a different slide, both of them were very visible to people. Can somebody confirm that? Cool, cool. Welcome, guys. I think there's two more people. That's great. Thank you for chipping in. Do get your friends. We are about to start in another 2 3 minutes. Grab a drink, or if you want to practice along with, we'll tell you how to do that as well. So, any questions from anyone? Like how? No, nothing so far. That's okay. That's pretty okay. Let's see how to make this bigger. Okay, no, I would want that option. Uh, let's do a quick tweet about the fact. Oh, uh, so we live stream every Sunday. So in case there's one of you who would want to join in or want to contribute towards topic, feel free to just post it in the chat, and we'll take that up. From next session onwards, we are probably going to stick to the exact time, like starting at 10 p.m. because I just take a couple of 10 minutes buffer to what do we say to test out the system and iron out my screen sharing and things like that. But I think after 2 3 sessions, I have sorted it out. So we should begin. So, guys, would you mind introducing yourself? Anybody who wants to introduce yourself to the group? Specifically, if you have a question, that would be even more interesting. I can see that number of people is changing between 4 and 6. Don't know where are people going towards. Okay, so we will start and I'll just set the agenda once again. So we are going to be talking about container technology today, and containers are something which are very widely used these days. They are almost the de facto standard for doing deployments, and they are relatively a new introduction to the deployment ecosystem. A lot of organizations still follow the traditional way. However, containers are very, very nimble units, and they kind of speed up and accelerate application development like crazy. Uh, so to define a container, right, we'll just take a small stab at the definition, and then we would go on the slides. So a container is a standard unit of software that packages of code and all the dependencies. What it means is that everything that you need to run your software, be it libraries, be it assets, be it application code, all of them are packaged together along with the runtime environment. So you basically bundle them all together, and the closest analogy I could think of is fat jar, which used to be a concept in Java. So, however, containers are probably much more robust in that sense, and the packaging is extremely nimble there. And what it contains is like an ISO file that we used to have before, right? It is standalone. It is executable. It is executable in the sense that if you package a container and you have a container runtime environment like Docker, it will run everywhere. It will pretty much run everywhere, and the module, the image itself will have all the code, runtime, tools, system libraries, and settings. Everything is just available in the container ecosystem itself. All right. I'm going to now start my screen share, and we'll get under the core of stuff. All right. A small disclaimer, which I usually begin all my presentations. So the way this session is going to be taking place is I'm going to run through slides for a while, and then I'm gonna do a little bit of notes making and explanation, and I could be switching in between, and then finally we'll go over to a live demo. All right. Now, when you deploy something, right, there's too many different mechanisms. There's so many different type of programming languages. There's so many different kinds of technologies out there. For example, people in Python world, they have requirements file, right, and there you put Python packages and the variants and all that. Typically, the machine learning ecosystem. In web development, it's even larger, right? The number of libraries you end up having just to build a API is humongous, and the list goes on, right? If you're working in a Java ecosystem, you'll have a lot of build dependencies and deploy dependencies out there. So it doesn't matter what programming language you use, there's all kinds of mechanisms that you have, and different kind of build system that you go through for your code. Now, once a code is built, either it could be a compiled language or an interpreted language, which implies there would be an executable file or some sort of a just-in-time interpreter, like in the case of Python. So the fundamental question that starts is, how many mechanisms do we need to know to deploy our code, right? And second is, how do we standardize them? Each programming language, each technology has its own flavor, and these two questions are effectively the starting points of these things, in my opinion, right? The first thing we are going to touch upon is container technology. Hey guys, for people who are just joining in, we have just started like probably 30 seconds before. Do get your friends. This is going to be an interesting session. We are going to be talking about containers. We will get into explanation session using some sort of a board and all, and then we'll look at a sample app. All right. So that's hosting technology and hosting infrastructure. That's what we are going to talking about beginning. Now, if you see the slide, and I'm going to just take a pointer here. Oh, sorry, this is not PowerPoint. If you see the way traditional hosting works, right, you have a server hardware, like which is the base hardware, where you have absolute fundamental physical infrastructure, which is of certain core, certain memory. Then you typically have some kind of a Linux kernel and distribution, where you have a operating system layer, be it Windows or Linux. Then you operate at some kind of runtime environment, which is to say JVM, which is the most popular one in enterprise software development. And then you have application software, which is application server. Now, this is loosely speaking Django or Flask for people who are from Python world. Node is another example. There could be any kind of application servers, right? Then you have configurations, and then you finally have the deployable unit. Now, this is the usual traditional hosting stack. And there's all kinds of complexities involved when you work at an infrastructure and deployment level, which is different problem compared to development. Now, this is not something which is tradition. I'm not sure, but wasn't taught to us in college. However, there's a lot of stuff that you need to worry about when you try to deploy something, right? For example, how do you make sure that the OS that you have is always up to date? And the cascading impact of that is when you upgrade an OS, you need to worry about the language and the runtime and libraries because of support. Now, how do you kind of differentiate different kind of computing needs? For instance, how do you work with compute jobs versus how do you work with database jobs, right? And all of these challenges are very popular in traditional hosting. To add, the world of machine learning has added more complexity. The world of AI has added more complexity. Now, machine learning training is something that you are expected to do intermittently. It's not always happening, and there's not a fixed life cycle to it. It's in the sense of that it can be ad hoc or it can be scheduled. Different kind of scenarios exist which require a much more flexible deployment management, right? So that's some premise building. Now, one of the principles that led to the evolution of container ecosystem, and I'm just going to skip the slides in between because some of them are not so important. If you think about it, this layer, right, this layer where you had a redundant lot of guest operating systems. So if you have three virtual machines, you need to have three different guest OSs, right? And that automatically implies that a lot of infrastructure is wasted because each OS will have fixed memory, fixed compute, and even if you're using it or not, right? Though a lot of virtualization softwares these days have enabled, what do we say, the shared model. However, this is a layer which can be looked at in the form of separation. All right. Now, going forward, the way containerized systems work is pretty much this. So you have an infrastructure, then there's hypervisor, which is the virtualization layer, and then you have different virtual machines, which is to say that virtual machine A, B, and C, and you could be having apps running on each of them. So there's an app A, there's an app B, and app C, and each of them are running independently. Now, the downside of this design traditionally has been that you have to add an OS in all of them, right? There's though in some form, containers also contain a kind of operating system inside them, a stripped down version of it, but we're not going to get into that depths. The idea here is that the elasticity is very different. Now, if you look at the other design, which is on the other side, containers, you typically have infrastructure and an operating system and a container runtime environment, on top of which you can put multiple apps. Now, the beauty of this is elasticity. If your apps are not being used, let's say if app E and F are not being used, you can spin them down very easily, and app A, B, C, D can probably cover more room. So containers are much more elastic and dynamic to begin with. All right. Now, this is typically a general example of how it works for a Python application or a standard web application, let's say. Traditional OS, you have application 1, 2, and 3, different sort of. However, in a container ecosystem, what happens is you have a container, the base Linux container, which we'll look at. And then each of them can be individual container images, which is for different applications. So if you want to run on the same machine different programming languages, the configuration doesn't become a nightmare and the dependency management becomes relatively easy. So a lot of modern software development, be it nature of microservice based development, it is extremely largely made nimble or enabled by container ecosystem. And we'll talk more about that, how that works. We'll look at a web application and kind of try to deploy it now. So that's the whole idea of container ecosystem and how things are built, right? And we'll come to Docker very shortly because Docker is more of a company than a technology first. So but it is almost synonymous there too, right? Now this is what differentiates, and this is more or less from a preparation of an interview standpoint and conceptual understanding what is what, right? So where does a virtualization occur in containers? And virtualization means, if you guys have used, if you have a machine, you would have probably run something like a Oracle VirtualBox or things like that to install Ubuntu or some other OSs, right? So that's containers. Then at the virtual machine level, it's server hardware. What does a container abstract? It abstracts the application from OS. This is the key difference, right? This is the key differentiating factor. It is not a versus discussion where like virtual machines are bad and containers are good. Containers abstract application from the OSs, which enable the nimbleness. Virtual machines abstract OS from the hardware, right? And there are a lot of use cases where you would might to prefer virtual machines over containers, right? Guest environment density and typical boot time. I think boot time is a very important concept here. A container can typically be spun up in probably a couple of seconds, while to get a virtual machine up and running, it takes a relatively larger amount of time. All right. We are going to skip this. This is how containers are implemented. The C groups, namespaces, capabilities that we need to go into, but we're going to jump to the container terminology and slowly to more, what do we say, actual looking at containers. So for the folks who are here, are there any questions? Feel free to put in questions in the chat, guys. And if anybody of you are not subscribed to the channel, please do subscribe to the channel. That would mean a lot to me. All right, coming back to this, image is the packaged version of all the dependencies. I like to think of them ISO files, like we used to have probably 4 or 5 years back, where we will have an ISO file where everything is installed and we will kind of create. A lot of people who used to install games used to have ISO 1, 2, 3, 4 for game installations and all that. So ISO files are a good example of images. Effectively, they are packaged version of dependencies, and I'll show you by creating some. Container, the actual container, what is it? It is the running instance of a given image. A lot of people confuse between them. Image is the file that has all the information. When it runs, when it is instantiated, when it is allocated memory and compute, it is called a container, right? Engine simply implies that the host OS process that is responsible for unpacking and all that, and this is provided by Docker or any other runtime. There's a lot of other Docker container ecosystem. Volume is the storage that is used by the container image. And again, I'll show this live in the example. Registry is a service that contains and stores the image. Think of it as your Play Store or App Store for containers. And cluster is more of a advanced thing where you have multiple containers working in unison, right? So that's what is container. Now, how do you Dockerize your application? You develop your app, pretty much whichever language you want to have. You write a Docker file and you build it and pretty much run anywhere, right? And we are going to be looking at a couple of workflows in the slide first, and then I'm gonna be hopping over to doing this, and we'll talk about installing Docker and all that too. All right. So this is Docker, where you have a Docker file where all the source code sits and everything. There's the whole app. This could be sitting in your Git or local wherever, and you make it go through the build process, and a container A is created, which is pretty much this. It is pushed to a container registry, and which can be pulled further onto any other machine. That's the whole idea. Changes are just incremental in nature. If you want to make a small modification, automatically you can follow the same life cycle of it. And I'm going to jump over and show this process live, right? To begin with, a couple of key commands to understand. Docker build. Build is a command that is used to build an image from a Docker file, and we'll show you how that works. Docker images. This lists all images on a Docker host. Docker run runs an image. Docker PS is more of a command for listing and interacting with containers. Stop pretty much stops it. RM is just remove. RMI is remove the image. Now, if you would notice, all of the commands have just been prefixed by the word Docker, and everything else is relatively what it is doing. So build is build, run is run, etc. It's relatively straightforward, and I'm just gonna go and hop over to a demo now. All right. So we'll start in reverse order, and I'm gonna introduce you the App Store first. and how to install Docker. So you can just check the link out. I will paste the link in the chat. This is a link where you can just click download for Windows. It's available for Mac and Linux. If anybody is there on M1 processor, it's available for that too. It's evolving, but pretty good to use. Feel free to just check this link out and download if you already don't have it. Now this will allow you to download Docker Desktop, and once you download and install it, it's a relatively straightforward installation. You would get something like this. Sorry. One moment. Yeah, sorry. My screen should be now visible. So you would get something like this. This is the Docker interface. This is the whole setup for Docker. Now, as you can see, there's nothing running here. There are no images. I've just cleaned it before this session, and there are no volumes. This is just some stupid volume lying around. I can just remove it. Dev environments are a relatively new concept, but we'll look at that too shortly. All right. So we'll go to containers and apps, and the way to interact with Docker is using command line, relatively straightforward in a very easy way. Just before this session, I've kind of tried to work with Docker and get it. So we'll just show you Docker images. In my machine, there are no images. Docker ps-a, there are no containers running as well. All right. Now this implies that I have a working installation of Docker, and I think you can see that. It is the Docker version is 20.10. There are a couple of options that you can play around with in Docker. The most important thing is to make sure that you have using the WSL2 based engine checked in. If you are somebody who is working with a Windows based client, WSL2 is just way better than the traditional Hyper-V kind of a setup for virtualization. And all you need to do is just tick mark and apply and restart. Resources tabs you can just safely ignore. Engine is do not make any changes here. This just captures how Docker is supposed to work. You can enable a couple of experimental features which I do not have, and Kubernetes is also baked into it, but you need to enable it, and it's gonna just start creating a lot of stuff which we don't want to do today. All right, so this is how the interface looks. Now what I'm going to do is quickly hop over to my application code. All right, and this is a sample application which any of you can find in Docker tutorial. I've just downloaded it, and it's a very straightforward tutorial to work with. Now what I have is a to-do web application. This is a simple web application. All it does it brings up a nice UI and it allows you to create tasks and delete them once you're finished and all that. So it's a relatively simple to-do manager application. I have not written it. I have just downloaded it from the website. Now, as per the instructions, you can follow the same instructions in the UI, but I'm just going to give a live demonstration of it. Let's just probably increase the font a bit. All right, so this is the Docker file, and this is a standard syntax for a Docker file, right? There's a couple of key things to understand, and we'll take step-by-step approach, and then we'll hop on to creating the file and all that. So the first thing is you specify is from clause. Now from clause implies you set the base image. Now it is the first instruction, and what it simply means is what is the base image on top of it everything has to work. In this case, it is Node, which is using Alpine Linux. You can have other Linux variants. You can actually work with, you can select from Ubuntu and create it all from scratch, whatever works for you, right? The second thing is what you do is you run some installations inside it. So if you want to install something inside, you have a run command, and you can execute any command on top of the machine. So this could be getting upgrades, or this could be installing some languages or anything like that you want to do, right? Then you set the working directory, right? And this working directory becomes the path where everything is set. After this, what you do is copy your code to there. So from your local machine into containers app directory. So we started with a base image. we installed something, whatever we wanted to, and that something in this case is relatively small. We just added no cache, we get G++ compilers and things like that. And then what we did is we did a yarn install. If you're a Python person, you will do pip install. And we just installed production. Now what do we have there is, there's a lot of packages here in package.json, and it is basically trying to get all the libraries and dependencies that the app needs. Now that Docker file is just gonna run all of that, which is to say that once we install the base in the run command, now we are installing the actual dependencies the application needs. And this installation is happening inside the container, right? And then you run a command what to run. Like it could be Python something.py, or it could be node source index.js. This is called the entry point in the application. An entry point means this is how your code is going to enter, or this is how your application will start basically. All right. Now we are just going to follow a process. I did this a little while back, and I'm just gonna pull the same commands. So I'm gonna hit build again, and as you can see, a build process has been triggered. Now parallelly, if you see, there is nothing here right now, but okay, it finished. It finished really quickly because I had already done it once and most of the images were cached. Now if you see, it took 7 seconds, but the first time the build took 54 seconds. So basically what it means is the Alpine and the node variants and all of this stuff are cached already on my machine. So running the same command is just picking it from local, and the build is insanely faster. Now, if you see here, there's an image standing here, which was not there present before. There are no volumes and there are no containers. As I said, image is the ISO image, the packaged version of it. And an image simply implies that we have created the application. We have not yet run it. All right, and you can run it multiple ways. You can just click here, or you can just probably a much better so now I'm writing the run command, and the run command is docker run -dp inside port and outside port, and the name of the application, right? Whatever, sorry, the name of the container image. And once I press enter, you will see that an image has been created and it shows in use. There is an actual container here, and there are volumes that are okay. There's no volume. That's interesting. I thought there was a volume in this application. So just to show, this is the application that we needed to test. Now, hello people, how are you? Talking about containers. All right. This is a simple to-do app which has just been created. You can check mark that, you can delete that, and all those functionalities are there. And that's pretty much what a container does. Now I can stop this. I can just go to images. Sorry, I need to go to containers, and I can stop it from here interactively. You can also do the same thing from command. Or I can delete it. Now once I have stopped it, it is just in a stop state and my application will not be reachable. So if I just do a refresh, it's just not going to do anything. It's that application has been stopped. All right, so that's fundamentally what containers are and what they do. So I'll probably try to summarize this in a different form. And what we have tried to look at right now is, there's my machine. All right, this is a Windows machine. Let's say Windows. There's some OS running on top of it. Sorry, my bad. Windows is the OS. There's a Docker engine running on top of it. And I can deploy any container here, any programming language, any thing. And this is available on the browser. Right? Now I can take this if I want to run this in a different computer, somebody else's computer. Let's say this is a machine. I can take this image, I can put it into Docker Hub. which is what I was showing. Push in an hub, very similar to the Git process where you push something and pull something. And then this guy can pull it and run it in his browser. He need not build it. There's nothing that he has to do in order to run that. On his machine, it's just pre-configured and preset, and it's just going to work out of the box. So that's basically how Docker works. It is a relatively, I would say, easy concept and an easy setup. Let me probably go back to my slides and see if there's more depth I can try to add in the conversation. All right, so that's basically what container is and what containers do. Now, a couple of more things to talk about and be aware of when we look at containers. Now, just to do a quick recap, where are we? We have looked at what containers are at a high level, and we've looked at an application code and how Docker file, what's the role of Docker file. And I've just tried to create a sample application, and that was kind of working. Now I'm going to look at what are the technologies that you need to be aware of post once you learn Docker, right? Because Docker is just running one application. There's a lot of scenarios where you need to worry about more things, and I want to talk about that in the next couple of minutes, right? Now, if we look at what we have achieved, we started with a traditional deployment. We have talked a little bit about virtualization, which is what the modern way of doing was creating a virtual machine and all that. Then we have moved to a containerized deployment. And have we answered all the questions really that we begin with? Right? Let's do a quick check. Now, how do I keep my operating system updated without causing an application downtime? This can be achieved with containers. Though there's a small catch when it comes to container orchestration, but we have achieved this. How do we update, rollback our application without causing a downtime? This is something that we have not been able to solve with containers. Containers alone will not give me this. How do we provide a disaster recovery capability, which means that if my container goes down for whatsoever reason, is my system, is my website going to suffer? How do I make sure my compute jobs are independent and they don't hurt other kind of jobs, database, cache, whatever? Uh, Isolation, we have achieved isolation, right? And how do I package a little more workload onto less machines? That is not 100% sure, right? So containers alone are not the answer, right? What we need, what you need to be aware of is there's little more required than just isolation. You need to be having a technology that can enable scheduling where it will help you understand where my containers would run. More than where, I think that's a typo. It's more to do with when my containers would run. There's a life cycle and health management where if my containers have failed or there's some sort of failure, bring them back again. How do we upgrade them, right? How do we independently isolate them and look at them? How do we scale them? The security aspect of it, right? Scan the container images. How do we load balance it? How do we associate more persistent storage? Because one of the downside of containers is when a container goes down, well, it goes down, everything is lost. How do we log and track it, right? And the idea is that most of these questions cannot be answered by container alone. And that's where you have container orchestration engines. Container orchestration engines, the two of the most popular ones are Docker Swarm and Kubernetes. There's more, there's Rocket, there's Containerd, there's Mesos, which is also a container orchestration engine. However, Kubernetes is the one which is probably the gold standard in the industry. Now, Kubernetes fundamentally provides you a framework to run distributed applications. It takes care of all of the things that we talked in the previous slide. It takes care of scheduling, lifecycle and health, upgrade, rollbacks, isolation, scaling, everything, right? It takes care of all of these stuff. And that's what makes the whole packaging game more. So if you're one of those people who are targeting machine learning, or if you're targeting engineering or DevOps kind of ecosystem, Kubernetes is a very, very good skill to learn. Now, what couple of things to remember about Kubernetes is it does not deploy source code and does not build your system. It is not a build management, nor it is a deployment system. Kubernetes is a orchestrator. It enables these things, but it will not do it for you. You will have to make sure that some technology, probably in the DevOps ecosystem like CI/CD, interacts with Kubernetes and enables the deployment and the build processes, right? It will not provide you application level services. What I mean by that is Kubernetes does not has no opinion about your software. It is not designed for it. There is nothing that it's going to enable in the form of frameworks, database, caches, things like that. So the architecture is purely your own. Kubernetes is not dictating anything. If you need any of these, you can have them containerized and run it. Right? So that's how Kubernetes functions. There is no dictate on logging, monitoring, and alerting solutions. It pretty much supports most out of the box. There's a default way, but you can override them with standard APIs that Kubernetes provides. It also does not provide a mandate or any form of a configuration language. You can work with YAML, you can work with JSON, pretty much these two are the standards. And that's what Kubernetes is not. I'm going to stop at Kubernetes architecture, just at a high level architecture, not to get into too much of depth and give a lot of information. But the way Kubernetes works is there are a lot of, there's an image registry, which is this, where all your images are saved. There are nodes, and these are machines. Typically on cloud, these are themselves virtual machines, right? And then there's a master node, which is interacting to this, or a main node. And these nodes kind of are connected in a master slave architecture. Kubernetes exposes a lot of APIs. A component of Kubernetes is called API server. And that is what is fundamentally used to either provide interface to UI or to interact with Kubernetes in command line. It is a relatively large technology. It is probably not possible for a one person to be aware of all the aspects of Kubernetes, though you can try to learn them and be aware of them. But as an expertise, it is something that probably is not a good idea to get into it. It's a data center level technology. It's a relatively heavy technology to talk about it, right? So that's pretty much it, what Kubernetes does, and that's pretty much the function for Kubernetes. I'm going to stop here and just talk about what are the key things that Kubernetes enables in general. So there's a cluster, which is a collection of hosts, which is a collection of hosts that aggregate all the resources. So a cluster means there's a couple of nodes, and you're trying to make it as a pool to probably formulate a singular use case, or find a way of grouping it. It's entirely up to you. Then there's master, which is pretty much a collection of components that make the control plane, that is what is going to control everything in Kubernetes. Node is a single machine in the cluster. There are two more concepts called pods. A pod is the smallest unit where you typically inside which containers run, and there's another concept called namespaces, which is a logical grouping of environments and logical grouping of setup. It's a method for scoping your requirements into the cluster. So that's how Kubernetes functions. You typically have a master, then there are nodes, you create a cluster, and you create namespaces inside which pods run. So yeah, that's pretty much a very short wrap on Kubernetes as well. That's pretty much what I wanted to talk about, guys, and that's pretty much what I had for the day. Please do remember that I talk on technology data every Sunday at 10 p.m. If there's a topic that you would like to listen, or you would want me to talk about, please drop that in the comments. And if you have not subscribed my channel, please do that. Thank you. Thank you for your time. Bye bye.